This is analyzing baseball data in R, Chapter 8. We're moving right along here. This is career trajectories. So let me just share my screen or my window. I think it's this one. Yeah. Let me move all these things. I don't. Does that look visible to everybody? Oh, see, I told you to go crazy. Okay, so this is a, come on, man. Dog's gonna drive me crazy. I apologize. Let me just go check on him real quick. I apologize. Everybody take a 5-minute breather and hopefully get our lovely host to delete this segment of the video. I apologize. Hang on a second. It's bad timing. Okay, I thank you for your patience on that. Hopefully, John the geek can dial that. Actually, maybe if I put like a restart in the thing, I'll just put that in there. Try to tell him about it. Okay. I don't know if that'll work or just cause more problems for the automated system or not. Hopefully, the former, not the latter. I'll try to remember to tell him about that. So this is chapter 8 on career trajectories. And the main objectives for this chapter, as far as I could tell, anyone can have their own opinion on this, is a kind of refresh on doing regression models with LM and R. And also, of course, to study player career trajectories. And as a kind of warm up, we start out with Mickey Mantle's trajectory. And so this uses just the Lawman database, which is nice because that's built in. I mean, not built in, it's a library that you don't have to do any extra work to get the data for. You just have to have the library. Let me just read here. And so we can just pull out, we can use the people table to find Mickey Mantle's ID, pull that out, and then pull in all the batting data. There's an issue the book mentions about some of the statistics don't exist in the early data, so he just shoves in zeros in there without further justification, which is fine, I suppose, for this. I kind of everything is kind of here is just kind of a quick look at this. I imagine if you were going to really study this, there's a lot more work you would want to do here. I'll try to point out another place where I see that is most likely the case as well. So, in any event, we want to calculate this uh, OBP, which is OBS plus slugging. What does OBP stand for? Anyone know? Can't think of what it stands for now. Oh, I guess it's OBS plus slugging, but why is that POP is for the plus? Is that basically what it is?
Oh, OB, wait.
OPS, what this should say. That's the problem. It's just a typo.
Yeah.
OPP is on base percentage. So yeah.
On
So
base.
yeah. So this I meant to say OPS actually is in here. Here's the code. So calculate this slugging average, which has to do with how many times you get on base, or I guess your average base number in some sense, and then your on base percentage, time fraction economic base, and then add those together. This kind of arbitrarily added together, but this has been found historically to provide a good measure of batter performance, this OPS, which stands for basically on base percentage plus slugging. The S is slugging. I think that's basically what it means, right? It's OPS. Okay. We also calculate their year using this convention, which I forget how, but something to do with if it's in later than June, then their birthday is also going to be in June, I guess, or July, for the purposes of calculating the age. And I think if I remember that correctly, correct me if I'm wrong. In any event, the age is computed and then the OPS. Those are the main things we care about here is age and OPS. The rest is kind of secondary. So with that, we can then do a little scatter plot of Mickey Mantle's OPS versus how old he was. And we can see there's kind of an arc here. Looks like somewhere around 27-ish, 26-ish, maybe 26-ish. He had his peak and then, which is pretty good, well, it looks like more than 1.1, and then fell off as he got older. And so we can do better than just eyeballing it. We can try to fit this to a parabola. The idea is that we should say, hey, we'll just say that there's a kind of parabolic shape to it. So the OPS is a function of age should be has some maximum, and then it decreases quadratically away from some peak age. Yeah, Iron Judge 1.2, that's awesome. So, and this is the way I would parameterize it, but this you could actually fit this directly, but it's nonlinear in the parameters the way I wrote it, but you can rewrite it in the way the book does as a linear model like this, and then you just arbitrarily off, not arbitrarily, but just to center things slightly center-ish. It's always better to center things a bit. So subtracting 30 kind of centers the age a little bit. And then you can just do the algebra to calculate that the peak age from that is these formulas. This is what he'll use. In LM, you can fit this model, because it now is a linear model, with this formula. The I here means just like, I forget why they call it I, but it just means do this, literally do this. Otherwise, otherwise it would do all kinds of extra terms or generate all kinds of extra. Like normally, if you write age times age, it generates. Uh, Actually, I'm not sure what it does to age. So normally, when you multiply things in these formulas, it creates interaction terms, right? And it tries to figures out both the interaction terms and also the linear terms. That's not what we want here. I'm not sure if we do age squared, what it does. Does anyone know? If I didn't have the I, if I just did age squared, does it try to make like a 2 times age plus age colon age or something? I don't know. Anyone offhand? Or does it do like a orthogonal polynomial or something like that? I don't know. Any event, this is what you have to do. If you really want the formula to be this, you have to put it in with an I. So it means it's like literally doing that. I have to look that up to see what happens if you don't put the I there in that case. So we can do that with the Mickey Mantle data. This is on the book. It's pretty straightforward, I think, right? So you just do fit model. So he defines a function called fit model that will fit it, pull out the coefficients, calculate the max from those coefficients, the formulas we just had before, calculate the maximum age as well as the max OPS. And then shove them all into a nice little list to return it back. So we can call that and then pull out, for example, we'll pull out the fit and then look at the coefficients for that directly. And these are the coefficients. Oh, isolates. That's what I always wonder what I stood for. Isolates. Okay. Or insulates. Ah, good to know. Right. Because otherwise they are special formula operators. Okay. I got you. Cool. Thanks. I appreciate that. Isolates. I gotta remember that. So I always think it was like identity operator, like I do identity this. That's just made that up. I don't know where I got that from. So in any event, we can get the actual coefficients from the fit, the A, B, and C. That's what these are. What we really want is the computed maximum age, which is 27, and his peak OPS, which was about 1.08 from that. So that's pretty straightforward. We can then plot down on top. So he uses ggplot, and if you use ggplot with method lm for the smooth, it'll just do its own polynomial fit, which you can give the formula for. This is another way to write the polynomial fit. In this case, it actually will use, I think, orthogonal polynomials. What it doesn't really matter. It just has a second degree polynomial. You could have used this as well in the other, in our LM, but then we would have had trouble pulling out the coefficients because I think they use orthogonal polynomials for this. So there it is, the same line. Here's the line how it fits through the dotted points. Beautiful. We love that. Okay, moving on. Any comments about that? Let's see. Turns out you can look at the full fit summary from that fit. There's more than just the coefficients that come out of it. You also can get what, for example, the median, the statistics on the residuals. You can get estimated standard errors on the coefficients, as well as like p-values and things if you want. R squared. I guess the one thing the book points out is this R squared of about 0.6 or maybe 0.55, usually adjusted R squared, which I think takes out the degrees of freedom, is saying that about 60% of the variation OPS is explained. I put that in quotes because like that just means it's well, I guess explained by that curve. So the curviness of the curve, which makes sense, right? Because if you look back at the, I'm sorry, look at the curve, you can see that, yeah, if I imagine, there's this much variation, and then if I go around the curve, there's significantly less variation around the curve. So the curve does explain a lot of the variation in the data. It's just one of the goodness of fit measures you can use in these kinds of fits. Okay, so then any comments on the section 8.1 from anybody?
Ron, I just have a comment.
Yes, please, of course.
What's interesting that the author, Jim,
Yeah.
selected Mickey Mantle because I don't know if you have watched the Ken Burns, baseball history.
Some of it actually, I need to get back to that.
It's about 13 episodes.
Yeah.
It's pretty deep.
Yeah, I forgot about that. I gotta get back to that.
Yeah, but I remember that one was was following the Mantle's trajectory, and one of the things that I didn't know about him is that he usually played with injuries. Okay, he had a lot of injuries in his joints, muscles, and all that, and that was not very very well known for the public. But the people that knew him, especially Maris, okay, who was playing with him more or less at the same time, Roger Maris, the one that did the 61 runs in a decade, breaking Ruth's record. He said, later he said that it was a miracle that Mickey Mantle could perform at that level with those kinds of ailments, in his body. And that speaks a lot for, his commitment, his, sheer will, and just, playing the game, which is, remarkable. I mean, if you don't watch, any of the episodes, try to watch that one, okay, about Mickey Mantle,
Yeah, it sounds like
it's something that, really gives you, really gives you kind of, a love for the game. I don't know. Okay.
Yeah, I'll definitely
that's my comment on.
Appreciate that. No, that's a good resource. I've watched a couple of those. It's actually been a while since I watched them, so I have to get back and dig into that again. So this next section, we're going to look at comparing trajectories of what he calls similar players. So we're going to group players are certainly similar if they're in the same position, but it'd be useful to look at like how similar are the trajectories of players that not only have the same position, but have other characteristics in common. And Bill James developed this measure of similarity that the book talks about, using position is a big one, but also other things like how many games played, how many at-bats, hits, it's all those different statistics. So if they have very similar statistics in every other way, then how well do their trajectories compare? And so so first we have to grab all the data. So we're going to take the batting data again. And first thing he does, he restricts us to only batters that have had significant career, not like little people who only played a short time, but people who only had 2,000 at bats. So we get, so that's one piece of selection right there. So we're going to conditional on the 2,000 at bats. And then to assign them a position, we're going to use the position they most often played at. And that's what this section of code does. Let's see what else does he do here. And then he computes their career statistics. That is how many games, all the different things we've done, the batting average, the slugging average, all the rest of the things for the entire career. and then combines that with their value for their position, which is again termed by Bill James for calculating similarity. So I guess the idea is that a first baseman and a catcher are very, very different, but a first outfielder and a first baseman aren't as different as those two are. And I don't know how he made those numbers up, but I'm sure that one thing I've noticed reading Bill James things, he's not afraid to like do stuff like this. I would be always like, well, I can't just make up things, but he seems to have no problem with making up these kind of things and making them work. What do you call these kinds of models? Empirical model, I guess. Kind of an empirical model, right? So I think there's another word I'm trying to think of, but anyway. Right, so that's that part. And so then it goes through and computes for all these career statistics. These are the career statistics now, how similar the players are. And these it's just basically the differences, right? For each player. So you pick out some player, like Mickey Mantle, and you say, okay, find me 10 players that are similar to Mickey Mantle in this way. So we just look at all these differences between all these statistics, and they get scaled by different amounts. Again, numbers that Bill James found would work best, probably based a little bit on his gut feeling about how important these are, and probably based on looking at things that turned out to be similar and saying, does that make sense? And then finally, we also look at this difference in position, and all these things are subtracted from 1,000. So 1,000, if you get 1,000, you're very, very different because you must be off on all these, right? Or no, that's the other way around. If you're 1,000, you're very close because you haven't subtracted any of these. Yeah, so that's right. So 1,000 is perfect similarity, and then it goes down from there as you subtract off all these differences. I don't know if it's possible to go negative. There's nothing here that would make it stop from being negative in any event. So then we average, we arrange those, sort them by descending score, and then take off the first n that we asked for. That's what this function does. It's given in the book. So if you run that for Mickey Mantle, you find these guys, and the book tells you the full names of these guys, but I don't know who they are, but well, I guess this one we know. That one we know, Sammy Sosa, but the rest of them I don't recognize right away who they are. But this Sammy Sosa apparently is very similar to Mickey Mantle, according to this calculation, because he had similar career stats. Kind of interesting. So now we're not quite done because we've got that. We have to also now compute now for every season these players OPS and the age, so we can actually compute these trajectories for each one of these similar players. And so one issue that comes up is that players might play for different teams, so they just combines all the and they get separated out. So oh yeah, that's right. The book does mention that it's on the chat here. The book does mention that these similarity scores are available also on the baseball reference pages, so that's kind of cool. I actually never heard of this concept, so I may want to dig into that a little further. In any event, so we're just going to combine all the different player stints into one, then calculate their stats for each season, calculate the OPS, add the age back in. I don't know why he uses, must be a reason why he did this all over again. So he defined a function in the first section to do this, but we're just going to do it again instead of, reusing the code. Sometimes, I mean, I know people say, don't repeat yourself, the drive principle, but sometimes it is more expedient sometimes to repeat yourself if you're doing a one-off thing. I know it's a bad habit, but sometimes it does happen. Okay, so now he's going to take a look and plot all these trajectories for take a player, take 5 similar players using our function for the similarity thing, right? And then we're going to just plot their trajectories. And no, we're not actually we're actually using a different formula this time for whatever reason, but we're going to use the GM Smooth from ggplot to do the fitting for this graphical purposes. And this is those 6 similar players. There's Sammy Sosa. Actually, I guess there's Mickey Mantles. They kind of look. So he peaked later, of course, but I mean, his curve is similar sharpness, but he peaked later. That may be a sign of the times, something to think about. But okay, I don't know. I mean, I don't know what we're supposed to take away from this exactly. They're different. Okay, that's all I get out of that. I don't really see. I'm not sure that's why I put this takeaways. I'm not sure. I didn't get out of the chapter what the point of this really was. Anyone else? I guess I could also look at the other possibility, which is Derek Jeter. Here's players that are similar to Derek Jeter. And this guy had a much flatter career. Not that great on OPS, I guess, compared to these other guys. Look at this guy. Ooh, right up, real sharp curve. And died off after that. So I don't know.
Also,
book
sometimes you can see that they peak at different,
Yeah.
different periods. Sometimes, early in the career, then or later, or kind of flat.
Yeah, I mean that's true, but the point of this, I think, was to look at similar players and maybe we see, but I don't see that. I guess we'd have to also look at dissimilar players to see if they're also the same. We didn't do that. Maybe that's a good exercise to read it, but these similar players don't look any different than probably in my mind to 9 random players we probably grabbed. Maybe I don't know. So I'm not sure what the exercise was supposed to tell us. That's I was hoping maybe somebody else. That was one thing I wanted to hope maybe sales had some comments on that. But if you do have some comments later too, feel free to think about it and put it in Slack. But
I think at least for these, it probably makes sense that they're all similar length of career because I think at least with the similarity calculation, a lot
That's
of
in
it's
there.
counting stats.
Yeah.
So that like Jeter and Mantle both had long careers, so it would make sense that these other people would as well.
Cal Ripken is a famous guy. Okay.
The other one was
Uh-huh.
interesting. I think Frank Thomas on the previous plot.
Yeah. Yeah.
It was just
Early. And then
straight downward, yeah.
Yeah. When did he play?
He was early 2000s, I believe.
Hmm.
Um,
It looks like he had a late start, right? Like 23
yeah,
or something.
oh, sorry, 90s and early 2000s.
Okay.
I think that's the same. Yeah, he started at 22.
Okay, that makes sense. That's what we see here. Yeah. Interesting.
Here's his baseball reference page.
Cool.
Yeah, 1990 to 2008.
I guess this is all major league though, right? The data we're looking at, doesn't remember. These are all major league. Unless they're major league, yeah. So maybe he just had a late start, like he was in minors for a long time, and then finally, like they said, "Hey, wait a minute, this guy's doing pretty good. We should bring him up." And he was doing well for a while, then started falling off.
Mickey starting at 18, that's uncommon
These
in
days,
this day and age.
yeah. Oh, so yeah. So one other thing he does then he says, okay, let's go ahead and take all the players and summarize them by peak age and curvature together, and you get a plot like this. And this is I don't know what are these. I forgot now. Are these similar players? I kind of forgot now. Yeah, sorry. This comes from these are the same 9 players that were shown in the previous thing. Weirdly enough, I don't know. This might be just a thing. I would have thought to do this, but he instead of just using the data that he generates, he just pulls the data directly out of the plot again. Just kind of interesting thing to do. And then uses that to calculate, and then makes a new regression on that. I wonder if it's possible to pull the regression lines out of the plot too, but he makes a new regression line on it this way. I guess he wants to do this so he can calculate the peaks and everything. Yeah, and then calculate the maximum ages and things again. Another repeating of the same code. But so then so he plots these are the 9 players, and we can see that interestingly, there's kind of a correlation between like core. I don't think the book mentions it, but I did notice there's kind of a trend between peaking later and having a more gentle curve, which makes sense, right? If you're going to start at a similar age and you're going to peak later, you're going to have a more gentle curve. I mean, that just makes sense to me. If everybody starts kind of at the same age nowadays, more or less, a few years. Oh, there's only a few years difference here, so maybe that's kind of not such a great observation. So the next thing, well, speaking of things changing with time, the next section looks at the general patterns of this peak age, like how have peak ages varied across time, and does peak age vary with the number of at bats? So the first one, we have to do some data preparation. I won't bore you with all these details. Let me see, is there anything important to pull out of here though? Well, first thing he wants to do is make sure that these are players that have had a complete career. So we don't want to try to fit any players that are kind of mid-career for this. So he cuts those out. Then he calculates when their middle of their career was. So that's going to be our identifying. We're going to associate the player with that year. Then calculate for each one of these players their peak age, do the fit, and calculate their peak age and I guess only peak age. So yeah. So now we've got basically a data frame now with peak age and the mid year and the position they're playing. I actually added this in because it was just too much for me to repeat myself yet again for the last section when we already done all the calculations. So I just said, hey, let's just throw the position on this table. So when we do the next section where we're talking about position, I'll have it already to go. I already have the data calculated. So first, this patterns of peak age over time. Again, we're going to plot the coefficients now, right? This beta coefficients is this table I just talked about that has the ages and the positions and the mid years and the peak age, right? Yeah. So this is what this looks like. This is now the scatter plot for all these people from 1880 to 2000 of their peak age. And this is just a low S plot on top of it. And I don't know, the book claims that there's a slight gradual increase. I guess, I don't know. It seems pretty flat to me. Maybe there's a slight gradual increase. There's certainly some kind of thing happening at the end, maybe with the low S, but given the scatter on this, I'm not sure how much confidence I'd have in saying that there's a significant trend. This is one of those things, if I really was interested, I'd want to look at a little more carefully. Maybe put in some more predictors, maybe try to do I'd probably use a Bayesian BMS model or something like that to try to get a better understanding of the uncertainties here. Probably do a grouped, heterogeneous, a hierarchical model, sorry, that takes into account position, that kind of thing. But maybe he says there's a gradual increase. I don't know. I'll believe him. And then finally, the same thing is done here with the at-bats, just using the same data table, calculating the log of the at-bats and plotting that. He says just to make them so they cluster better, I guess. But this is a log base 2. The career at-bats could, so 10, 2 to 11, 2 to 12, 2 to 13. And here you can see that there is, I guess he's saying longer careers tend to peak at a higher age. That makes, again, perfect sense to what we said before, that if you peak early, then you're going to probably be finished early as well, right? If the curvature holds up. So anyway, again, that's something you probably want to look at more carefully. The other thing you want to probably look at more carefully is to make sure that these things all have like negative second derivatives. Like some of these peak ages might be the position of a valley, because some of these guys have such shallow careers that might go the other way. That should be checked as well. So some of these might not even be valid peak ages. We didn't really check that. So just something to worry about, I guess, if you're going to really dig into this. So finally, the last section is on fielding position. And like I said, we already have the fits. So I just, he wanted to do from 1985 to 1995. So I just grabbed those, filter down to just the position, the fielders, and that's basically it. Just plot it, right? Yeah. So this is just a jitter plot, standard kind of, jitter plot that you can make, strip plot, and you can see absolutely nothing in this as far as I don't see a clear pattern to this at all. So is there some position dependent thing about peak age? I don't see I don't see that in here. Again, I think the way to do this, probably the right way, is to do a full regression model with mixed effects for take each player as a group essentially and do like some kind of mixed effects model like that and try to understand I did try to make an attack on that. I didn't get too far with it because it gets complicated because of the nonlinearity of this peak age thing. That's why I kind of wrote down a nonlinear model, because I did try like a nonlinear fit to try to better predict peak age as a grouped variable. I don't know. I'm not convinced that my results are correct, so probably not gonna share it with you. I did see that the first baseman in that fit, I did see that something about the first baseman tend to peak a little earlier than like outfielders, for example. That's about the only thing I could conclude. But you can't really see in this. But
I
Did
think
anyone-
it makes sense at least for like shortstop compared to catcher. It looks like quite a few more shortstops peaked early.
Yeah,
I'm just assuming uh, it's easier to make it to the big leagues as a shortstop compared to catcher.
that's a good point. Actually, it's interesting. There's a lot less variability in the catchers.
Yeah, it's a highly defensive position. I think if you look at like the most in demand defensive positions, catchers usually number one. Shortstop too, but that's more uh, geared towards athleticism.
Yeah,
Um, so yeah, that could be a
it is interesting. Two very important defensive. Like obviously, catcher is the most important. The second, another very important defensive position, first base, also doesn't have has almost none below 25. Like they didn't get these guys or hot shots. They don't trust them to take on the first base, right? So you can go sit in the outfield for a while, and then maybe mature your play a little bit. So interesting.
they grouped it by
True, that's true by most played position.
most starts or whatever. That's
Yeah,
so that could play
that's a good point too.
play a part of this.
Yeah, I didn't think about that. Did not think about that. I guess that's it. Some discussion points. I don't know. One thing I was thinking of maybe even again, you go too far on this, you can really. I mean, this is a big rabbit. Like any of these things, these can be a big rabbit hole. I didn't go through the further reading to see like how deep that rabbit hole goes, but I did think about this a little bit. One of the things I thought, well, what about it's quadratic a little bit too naive? Maybe you could use something else like Gaussian process or something on their career and try to understand it that way. Um, and the other thing I thought of was, did anybody do? I didn't do any of the exercises. I apologize. I didn't have the time. Did anyone look at the exercises that they want to share with any of that? I'll take it you guys are all as eager to do the exercises. I mean, all the free time like I had to do the exercises. uh, yeah, I didn't have any time to do the exercises. I barely had time to get these notes together. So I did run all the code in the chapter though. It all works. So if you do get around to doing that, it all does work pretty nicely. Okay, I think that's all I had. Anyone else have anything else about the chapter they want to share? About baseball trajectory, career trajectory. We didn't look at pitchers. I mean, that's something that happens in the exercises. I didn't even look what the exercises had. Oh, I can look in the book, but I'll do it later. And I believe who's got next week? Can someone remind me?
Derek, have next week talking about simulating games.
Awesome. Oh, that's gonna be a fun chapter. Yeah, like a little state machine simulation. I'm looking forward to that. Cool. Anyone else have any other comments? Should we just make sure we actually have the. So we do need somebody to take on chapter 10, exploring streaky performances, which I assume has nothing to do with people running naked on through the field, but rather has to do with people having hot streaks and cold streaks as well, right? What do they call it in soccer? They had a word for it in that Ted Lasso show. Can't remember what it was now. Anyway, when you have that problem where you have a bad streak or a hot streak, that's probably what that's going to be. So if somebody else take that on, please feel free to think about it, sign up. When you go to the spreadsheet, actually, hold on, people watching the video don't hear all